the secret science behind human survival. At this very moment, 20,000 feet above sea level, Tibetan highlanders are breathing normally while you, or I, would be suffering altitude sickness. Their bodies have physically evolved larger lungs and specialized blood cells that scientists once thought impossible. What if I told you humans have developed superpowers to survive in environments that should kill us? How did these remarkable adaptations come to be? In the next 15 minutes, you'll discover how certain populations can hold their breath underwater for over 10 minutes, survive in minus 60 degrees Fahrenheit temperatures with minimal clothing, or extract water from seemingly barren deserts, all through natural adaptations our species has developed over generations. The roof of a world. Life at 16,000 feet. What if your next breath contained 40% less oxygen than you're used to? Welcome to the Tibetan Plateau, a vast elevated region that stretches across 2.5 million square kilometers of Central Asia. Often called the roof of the world, this massive highland sits at an average elevation exceeding 16,000 feet above sea level, making it both the highest and largest plateau on Earth. To put this in perspective, standing on the Tibetan Plateau places you higher than the summit of nearly every mountain in the continental United States. The atmosphere at this altitude contains drastically less oxygen than what most humans experience. At sea level, oxygen makes up about 21% of the air, but the decreased atmospheric pressure at 16,000 feet means each breath delivers far less oxygen to your lungs. This creates potentially deadly conditions for the unprepared. When the typical human body encounters these conditions, it immediately begins to struggle. The first response is hyperventilation. Your breathing rate increases as your body desperately tries to compensate for the oxygen deficit. Your heart races, sometimes exceeding 100 beats per minute even at rest, attempting to circulate the limited oxygen throughout your body. Within hours, symptoms intensify. Splitting headaches develop as oxygen-starved brain tissue begins to swell. Nausea, vomiting, and extreme fatigue make even minor physical tasks exhausting. Cognitive functions deteriorate. Sleep becomes nearly impossible as your breathing pattern grows irregular, often including prolonged pauses that jolt you awake, gasping for air. For some visitors, the situation becomes life-threatening within days. High-altitude pulmonary edema can develop, causing shortness of breath even at rest and a persistent cough producing frothy sputum. Without immediate descent to lower elevation, this condition can be fatal within hours. Yet amid this celestial coliseum where the unprepared falter, a population of over 6 million people thrives. Elderly Tibetan villagers in their 80s and 90s tend to fields at elevations where mountain climbers require supplemental oxygen. Young children play vigorous games, running and laughing. Pregnant women carry babies to term and conditions where lowlanders experience high rates of miscarriage. Tibetan laborers routinely carry heavy loads up steep mountain paths without oxygen distress. The contrast between natives and visitors is stark. Tourists shuffle slowly through markets with oxygen canisters at their side. Local vendors energetically hawk their wares for hours without fatigue. Lowland visitors experience interrupted sleep despite weeks of careful acclimatization and medications. Tibetan hosts sleep soundly and wake refreshed. This represents a profound physiological difference, not merely mental toughness or superior fitness. This harsh environment presents challenges beyond oxygen scarcity. Winter temperatures plummet to minus 40 degrees Fahrenheit with fierce winds. Summer nights frequently drop below freezing, creating an extremely brief growing season. UV exposure on the plateau can be 40% higher than at sea level, causing rapid sunburn and increased cancer risk. Water resources are limited, with much of the region receiving less than 10 inches of precipitation annually. These combined challenges create an environment so hostile that Chinese scientists in the 1950s had to rotate personnel every few weeks due to deteriorating health. Yet Tibetan communities have continuously occupied these highlands for thousands of years, developing a perfectly calibrated way of life. Medical imaging reveals part of this remarkable adaptation. Tibetans typically have broader chests and enhanced diaphragm strength, allowing them to take in more air with each breath. Their breathing pattern is deeper and more efficient, extracting maximum oxygen from the thin air. The most puzzling aspect emerges when measuring blood oxygen levels. Despite identical environmental conditions, Tibetans maintain oxygen saturation levels of 85 to 90%, while visitors often drop below 80% even after weeks of acclimatization. The typical human response to high altitude involves producing more red blood cells to transport oxygen. Most visitors show dramatically increased hematocrit levels, sometimes exceeding 60% compared to the normal 45%. This compensatory response creates a dangerous side effect. Blood becomes thicker and more viscous, flowing more slowly and increasing the risk of clots. The risk of stroke, heart attack, and pulmonary embolism rises significantly, particularly during pregnancy. Here, Tibetan physiology demonstrates its most remarkable feature. Blood tests consistently show that Tibetans maintain normal or even lower than expected red blood cell counts despite the oxygen-poor environment. Their blood remains thin and flows freely, eliminating dangerous side effects while somehow maintaining adequate tissue oxygenation. Research revealed another adaptation. Nitric oxide levels in Tibetan subjects appeared in concentrations approximately 10 times higher than in lowlanders. This molecule causes blood vessels to dilate, allowing blood to reach peripheral tissues more efficiently without requiring dangerous increases in blood viscosity. For decades, these findings puzzled medical researchers. Every physiological principle suggested these people should suffer from chronic hypoxia, oxygen starvation, yet they showed none of the expected signs. Their bodies maintained normal function with oxygen levels that would trigger serious medical interventions in any hospital. Even more confounding, they accomplished this without the compensatory mechanisms observed in every other human population studied at altitude. What invisible adaptation allowed Tibetans to settle permanently in an environment that remains hostile to everyone else? The answer would ultimately be found in their genetic code, in a story of inheritance that stretches back to an extinct human species and an evolutionary process that worked at unprecedented speed. Genetic time capsule, the Denisovan connection. The answer to the Tibetan altitude mystery was hiding not in their physiology, but in their DNA, a 40,000-year-old genetic gift from a species of humans most people have never heard of. While researchers expected to find gradual adaptations accumulated over countless generations, what they discovered instead rewrote our understanding of human evolution. When scientists first began investigating the Tibetan high-altitude adaptation, they faced a perplexing timeline problem. Most significant evolutionary adaptations require tens or even hundreds of thousands of years to develop within a population. Yet archaeological evidence showed humans had only inhabited the Tibetan Plateau permanently for approximately 3,000 to 4,000 years. How could such profound physiological differences emerge in what amounts to a genetic blink of an eye? The first breakthrough came in 2010 when researchers identified that Tibetans possessed a unique variant of a gene called EPS1. This gene, sometimes called the super athlete gene, plays a crucial role in how the body responds to low oxygen environments. The variant found in Tibetans contained a complex pattern of mutations that appeared nowhere else in the modern human genome. Then in 2014, a team led by researchers from the University of California, Berkeley made an astonishing discovery. They compared the Tibetan EPS1 variant against genetic material available from extinct human species. The results stunned the scientific community. The closest match wasn't found in any modern humans, but in genetic material extracted from a 40,000-year-old finger bone discovered in a remote Siberian cave. That finger bone belonged to a member of a previously unknown human species that scientists named Denisovans, after the Denisova cave where the remains were found. Unlike Neanderthals, whose skeletal remains have been found across Europe and Asia, almost everything we know about Denisovans comes from DNA extracted from that single finger bone, a few teeth, and a jawbone fragment discovered years later in a Tibetan cave. This is a really clear-cut case where admixture with an extinct population has benefited a modern population, explained Rasmus Nielsen, who led the 2014 study. Without modern genetic sequencing technology, we would never have known the Denisovans existed at all, much less their crucial contribution to human adaptation. How did Denisovan DNA end up in the Tibetan genome? The evidence points to interbreeding between early modern humans and Denisovans sometime between 40,000 and 60,000 years ago, as our ancestors migrated across Asia. Genetic evidence suggests multiple instances of interbreeding with both Denisovans and Neanderthals in human prehistory. Initially, this genetic transfer would have been just one of many variations in the early human gene pool, conferring no immediate advantage to those living at lower elevations. The real evolutionary story began when human groups moved upward to the Tibetan Plateau. Suddenly, individuals carrying this Denisovan genetic variant had a tremendous survival advantage in the oxygen-scarce environment. The scientific detective work required to uncover this story represents one of the most fascinating examples of genetic archaeology. Researchers compared DNA sequences of modern Tibetans with neighboring populations, identifying segments that showed signs of strong natural selection, regions where a specific variant had spread rapidly. The EPS1 region stood out dramatically, showing signs of what geneticists call a selective sweep, where a beneficial mutation spreads quickly. The pattern was so extreme that it indicated one of the strongest cases of natural selection ever documented in humans. Within approximately 3,000 years, roughly 120 generations, this genetic variant went from being present in a small percentage of the population to nearly universal among Tibetans. The Denisovan version of EPS1 contains a cluster of mutations spanning approximately 32,700 base pairs of DNA, a complex sequence that would be extremely unlikely to arise independently through random mutation. It's difficult to come up with a scenario where you could get the same 32,700 mutations to occur randomly by chance, explained Nielsen. This discovery fundamentally alters how we view human evolution, suggesting that interbreeding between different human species provided crucial genetic material that allowed our species to adapt to extreme environments. Like an ancient key unlocking a door to survival, this inherited genetic code enabled humans to thrive where others could not. The EPS1 gene serves as a master regulator for the body's response to hypoxia, low oxygen conditions. When oxygen levels drop, the gene typically signals for increased production of red blood cells. While this helps in short-term adaptation, chronically elevated red blood cell levels lead to dangerous blood thickening in non-adapted people at high altitudes. The Denisovan variant modifies this response, allowing Tibetans to maintain normal hemoglobin concentrations despite the low oxygen environment. Instead of dangerous overproduction of red blood cells, Tibetans' bodies use available oxygen more efficiently, preventing the chronic mountain sickness that affects many non-Tibetans at high elevations. For Tibetan women, this adaptation proves crucial during pregnancy, when oxygen demands increase dramatically. While pregnancy at high altitudes often results in low birth weights and higher infant mortality among non-adapted populations, Tibetan women can successfully carry pregnancies without these complications. Genetic dating techniques suggest that the selective advantage was enormous. Those with the Denisovan version of EPS1 were significantly more likely to survive and reproduce. Computer models indicate that for such a variant to spread throughout a population in just 3,000 years, it must have increased survival rates by at least 10-20%, an extraordinarily strong selective pressure. Recent archaeological discoveries have found Denisovan remains in the Baishia Karst cave on the Tibetan Plateau itself, located at 10,760 feet above sea level. This indicates Denisovans had already adapted to high-altitude living long before modern humans arrived, passing along genetic adaptations already tested by thousands of years of high-altitude living. Through cutting-edge genetic archaeology and modern sequencing techniques, scientists continue to unravel not just the Tibetan adaptation mystery, but also how these physiological differences manifest in everyday life at extreme altitudes, a bridge between our genetic past and the cultural practices that have developed alongside these biological advantages. Blood and breath, the biological paradox. This ancient Denisovan DNA doesn't just alter Tibetan genes. It completely reverses what should be a universal human physiological response. When most human bodies encounter oxygen-poor environments, they immediately implement emergency protocols that medical science long considered essential for survival. But Tibetans do the opposite, challenging decades of established medical understanding. For nearly a century, textbooks have described a predictable human response to high altitude. Your body senses the oxygen shortage and dramatically increases red blood cell production. This makes perfect sense at first glance. If each red blood cell carries oxygen, and you have less oxygen available, producing more cellular carriers should solve the problem. It's like adding more delivery trucks when demand increases. This protective mechanism kicks in rapidly when lowlanders ascend to altitude. Specialized cells in the kidneys detect low oxygen and release erythropoietin EPO, the same hormone that some athletes abuse as a performance enhancer. Within days, hematocrit levels can rise significantly as bone marrow accelerates red blood cell production. What begins as an elegant solution becomes problematic over time. Blood thickens like honey left in the cold as more red cells pack the bloodstream. This condition, polycythemia, creates severe health risks. High-altitude polycythemia is essentially a maladaptive response, explains Dr. Tatum Simonson, a physiologist at UCSD. Blood viscosity increases dramatically, forcing the heart to work harder to pump this thicker fluid through the circulatory system. The consequences can be severe. Thickened blood moves sluggishly through capillaries, reducing oxygen delivery to tissues. It increases blood pressure, strains the heart, and raises risks for stroke, heart attack, and blood clots. During pregnancy, this thick blood struggles to navigate the placenta's tiny vessels, contributing to higher rates of pregnancy complications among non-adapted women. Tibetan physiology defies this conventional wisdom. Despite living where oxygen pressure is roughly 40% lower than at sea level, most Tibetans maintain hemoglobin concentrations comparable to people living at sea level. Their bodies have rejected what medical science long considered the primary survival mechanism for high-altitude living. When we first measured hemoglobin levels in Tibetan populations, we had to recheck our equipment, recalls Dr. Cynthia Beale, an anthropologist who has studied high-altitude populations extensively. It contradicted everything in the literature. Here were people thriving at elevations where others developed serious polycythemia, yet their red blood cell counts were completely normal. Sonam, a Tibetan mother of 3 who lives at 14,000 feet, exemplifies this adaptation. The doctors from the university were surprised by my blood tests during pregnancy, she says. They told me women from lowland areas often struggle here, but my body knows this altitude. This counterintuitive adaptation creates a mystery. How do Tibetans get enough oxygen without extra carriers? The answer lies in a comprehensive redesign of their respiratory and circulatory systems. Tibetan lungs differ structurally from lowland lungs in several critical ways. They have approximately 20% greater lung volume relative to body size, with more extensive bronchial branching patterns, creating greater surface area for gas exchange. Even the density of alveoli, the tiny air sacs where oxygen transfers into the bloodstream, is notably higher. Tibetans take deeper, more efficient breaths, rather than the rapid, shallow breathing lowlanders develop at altitude. This breathing pattern maximizes oxygen intake while conserving energy. Respiratory measurements show Tibetans extract approximately 40% more oxygen from each breath compared to non-adapted individuals. Their circulatory system shows remarkable transformation. Tibetans have developed wider blood vessels and a more extensive capillary network. This expanded circulatory infrastructure improves blood flow efficiency and oxygen delivery to tissues despite lower red blood cell concentrations. Biochemically, Tibetan blood contains substantially higher concentrations of nitric oxide, a molecule that dilates blood vessels and facilitates oxygen transfer. while lowlanders typically produce less nitric oxide at high altitudes, contributing to blood vessel constriction. Tibetans produce more, another inversion of the standard response. The Tibetan pattern completely inverts the standard human response to hypoxia, explains Dr. Peter Robbins of Oxford University. Instead of increasing oxygen carriers in the blood, they've enhanced every other aspect of the oxygen transport chain, from inhalation to vessel architecture to cellular extraction mechanisms. These adaptations particularly benefit Tibetan women during pregnancy. Research shows Tibetan women experience almost double the uterine artery diameter increase during pregnancy compared to non-adapted populations. This expanded capacity, combined with lower blood viscosity, ensures adequate oxygen delivery to the developing fetus. At the cellular level, Tibetan tissues demonstrate enhanced efficiency in oxygen utilization. Their mitochondria, the cellular power plants, show modifications that allow optimal function under low oxygen conditions. This means Tibetan tissues maintain normal metabolic activity with less oxygen than lowlander cells require. The genetic mechanism enabling this comprehensive physiological redesign centers on the EPS1 gene inherited from Denisovans. This gene acts as a master regulator of the body's hypoxia response, controlling numerous processes including red blood cell production, blood vessel development, and cellular metabolism. The Denisovan variant reprograms these responses, preventing red blood cell overproduction while enhancing alternative adaptive pathways. It's as if the Tibetan genome contains a different instruction manual for responding to oxygen shortage, prioritizing efficiency over emergency measures. Dr. Joseph Prashal, a hematologist who has studied Tibetan blood characteristics extensively, describes it as an entirely different strategy for managing limited oxygen resources. Rather than hoarding oxygen through increased red cell mass, they've optimized its delivery and utilization throughout the system. This adaptation has profound implications. The Tibetan approach to oxygen management may offer insights into treating conditions like chronic obstructive pulmonary disease, heart failure, and altitude sickness, as well as blood disorders characterized by overproduction of red blood cells. Agricultural innovation at the edge of possibility. Beyond their physiological adaptations, Tibetans faced an existential challenge that required equal ingenuity, finding ways to grow food in what agronomists consider nearly impossible conditions. While the human body can adapt to extract more oxygen from thin air, plants cannot evolve so quickly. The Tibetan Plateau presents a near-perfect storm of agricultural obstacles. Growing seasons shorter than 100 days, nighttime temperatures that routinely plunge below freezing even in summer months, and soil severely depleted of nutrients. A modern agronomist transported to the plateau would likely declare commercial agriculture impossible. Most staple crops require at least 120 frost-free days to reach maturity. In the highlands of Tibet, frost can occur during any month of the year, with the summer growing window often limited to just 90 days. The soil freezes solid for 8 months annually, preventing the decomposition and nutrient cycling that makes agriculture possible elsewhere. Water presents another paradox. Despite being the source region for Asia's major river systems, much of the plateau remains chronically water-stressed for agriculture. Precipitation arrives primarily as winter snow, with summer rains often coming in short, intense bursts that cause erosion. The thin atmosphere accelerates evaporation, quickly drying out fields unless water is carefully managed. Yet across this seemingly impossible landscape, Tibetan farmers cultivate nearly 2 million acres of crops annually, feeding millions of people. Their agricultural system represents one of humanity's most remarkable adaptations, cultural and technological rather than genetic. Consider Dorje, a farmer in the remote Changtang region. Like his ancestors, he constructs stone walls oriented east to west across his fields. These walls, often 2 to 3 feet high, absorb solar radiation during the day and radiate heat back to crops at night, raising temperatures enough to prevent frost damage during critical growing periods. The same walls disrupt the powerful winds that sweep down from higher elevations, creating sheltered zones where tender young plants can establish themselves. Field design itself represents centuries of environmental engineering. In the Shigatse Valley, farmers like Yangzum create small, irregular plots carefully positioned to capitalize on natural landscape features that offer protection. Her fields are slightly recessed below ground level, creating natural windbreaks and heat traps that raise ambient temperatures by several crucial degrees. The agricultural calendar reflects generations of precise observation. In Lesa's surrounding farmlands, Tenzin's family doesn't plant according to fixed dates, but watches for particular bird migrations, the emergence of certain insects, or the flowering of wild indicator plants that signal when soil temperatures have stabilized enough for specific crops.